class? Can somebody just let me know if that was the case?
Yes, sir.
Okay, yeah, so just take a recap of what we did in the previous class. We were talking about different types of constraint nodes as per the RFC 7228 that was by the Internet Standard Authority that kind of does this. It is called IETF. Okay, so and I also suggested that you people go and visit the website if you see something. You'll find a lot of interesting stuff there. And we found that there are three different classes which we usually find in case of constraint nodes, which are defined by the 7228. Okay, we saw that there are possibilities where you have very low amount of RAM which is available, flash and RAM availability, in which case they will be mostly very dumb kind of systems. Where you have very limited functionality built into them. So basically you will find these kind of class 0 devices coming out of the manufacturer, mostly pre-programmed, or you may have very little amount of programming ability built into these class 0 type systems. Okay, and class 1 systems you will find there will be more functionality that is built into this. So this is where you will find a lot of the microcontroller codes microcontrollers which are available to you. So you may have smaller amount of flash, but you can program them, you can make them work according to your wish. So you could be having something like MSP 430 or Arduino. Some versions of Arduino will have this kind of a system. So you can kind of implement certain amount of protocols in this, but still it will not be like your Raspberry Pi, where you have full functionality and you can implement as much complicated algorithms as you want. And then you have the class 2 type, which is basically most of the modern heavy duty microcontrollers that you are able to see now. So most of the automotive grade microcontrollers and most of the what you may call as the full function type devices that you will find in IoT applications will all be of class 2. Okay, so you can see they basically say that you can have more 50 to 250 KB of flash. So usually it can be more than that also. So typically they will be class 2 devices. And you will find, I'll just add something more here. 1 second. So this is one very important thing that you should be knowing. That is, we have talked about these things, but there is also another very important application that is required, which is typically how are you going to use power. Right, so you have as far as the constraint devices classes are available, you have C0, C1 and C2. Similarly, you have three different strategies for using power also. So please understand that you can have any combination of C and P together here, right? But the idea is that P0 is something which is basically normally off condition and it kind of wakes up whenever requirement happens. P1 is typically you use very low amount of energy and you transmit at very low frequencies. So whenever you are polling for the device, you will find that it is connected, but there will be a lot of latency and there is going to be very slow communication which is happening. Okay, and P2 is typically the case when you have the device which is always connected and you are kind of able to connect it to it at any point of time and request and get the data at any point of time. So typically you can have any P and C combinations here, right? So usually P0 is the one which is the most energy conserving type system, because you will only be using the board or microcontroller or the IoT device when requirement happens. Right, this is something like, say you have a on-off system. The system will kind of I think I told you in the beginning, there's something called a brownout in most of the microcontrollers, or sleep mode basically. So the idea is that the IoT device will be sleeping. It will wake up after a fixed interval of time, transmit, go back to sleep again. Okay, so that is what will happen with P0 systems. P1 systems, again, as we discussed, they will be using very little amount of energy to stay awake. But the problem is that functionality will also be like that only. They'll be transmitting very little amount of data so that overall power consumption is minimized. P2 is typically used when you have a lot of energy in the surroundings. That means it's either completely plugged in or it has got some other source of energy like solar or wind or something like that to power it up. So that is the difference between, that is how you talk about the classes of constraint devices and the power usage. So you can combine anything with anything here. So C0 can be combined with P0, C1 can be combined with P1, C2 P2, C0 P2, C1 P0, anything that you want. It's up to you. Okay, but typically you will find that the class 2 devices tend to be always on, because the data requirements for these devices will be, the applications will be like that. You will require continuous transmission and you will need to continuously poll those devices for data. So usually C2 P2 combination will be used. Okay, and C0 is typically in locations where you cannot access the device very quickly or something like that. So C0 P0 combination is also very popular. Can we go to the next slide? If there are any questions, go ahead, please. Hello?
Okay, so we can go to next.
Okay. So next we go to the constrained node networks, which is basically the idea of, like this is how we are proceeding. I just wanted to show you this. There are 9 things that we have to see. Now we have reached the constrained node networks. Okay. So now what we are looking at is the idea of lossy low power networks or low power lossy networks. Typically, the nodes that you make using constrained devices are going to be referred to as constrained node networks. Okay, so the requirements typically, I mean, like obviously you can understand that this is the issue. You have very low amount of power because you want to make sure that the devices last for a very long time. So power requirements are very stringent, and you have a problem of lossy networks. Why lossy? Because you have a lot of surrounding kind of equipment which could be interfering with this, and you have a lot of loss of data which is happening. Why? Because you have very little amount of resources which you can kind of allot to these kind of activities. If you have a lot of resources in your hand, like computational resources, or you have a lot of energy in your hand, you can go for error correction, you can go for security, you can go for a lot of other applications. Unfortunately, the problem is you are prioritizing energy, and you are also prioritizing the costs. So the trade-off that you get as a result of that is that your network will be lossy, right? It's like you make a very cheap network which kind of creates in low communication quality. That is the whole process. If you want a good network with very minimal losses, the network will become very costly. So the more costlier the network, the lesser losses it will have. The cheaper the network that you are setting up, the more losses it will have. But cost is a very important consideration in most of the IoT systems, as I said, because you could be having thousands of nodes sitting around, and even 1000 rupees increase in the cost of the node can lead to huge increases in the costs over the entire network, right? So you do not want to do that. You want to minimize the costs, and you want to make sure that the system is up and running. You can kind of handle some of the losses. So that is the idea. Unfortunately, as an engineer, you will have difficulty understanding that why would somebody want lossy network. the overriding concern in most of the business applications is that of cost. Eventually, everything depends upon cost only. So if you have constraints on the amount of money that can be spent or the return on investment that you are going to get, nobody will be interested in investing a lot of money which will not produce enough returns. So unfortunately, that's why you kind of, even when the technology is available, you end up implementing substandard networks, mainly because the costs do not allow it. Okay, so don't kind of worry about that. Like, there could be general question that some of you may be thinking that if there is so much loss in the network, why do you even set it up? Why don't you go for lossless networks or minimal loss type networks? The reason is cost. Okay. So what are the major requirements that you have if you are putting a constrained node network, or basically constrained node network? In other words, you can say a network of constrained nodes, basically, right? So that we have put it as constrained node networks. So three things are very important for constrained node networks. First is how much will be the data rate and what is going to be the throughput of the system. And second will be how much latency can we handle. Latency is typically delay. Okay. And the third is what is the kind of payload and what is the overhead requirements that will be there in the system that you are implementing. Right. So first we will go, we'll be looking at all these three aspects one by one. We'll first start with the data rate. Okay. So let's see. We will look at the data rate first. And you can see what is the data rate typically available for typical wireless standards. So you can see, I'm just comparing some of the most commonly used ones. The image was very small. I expanded it so it looks kind of hazy. But still, this is the idea. Okay, so you can see that some of the networks can have very high data rates as well as very high transmission distances. Right, so you can see a long LTE or 4G basically. So you have a lot of transmission capacity, you have a good range, you support audio, video, everything. Network is also public and the coverage is also quite good. Unfortunately, cost wise, they can be very prohibitive. So you can see some of them are kind of listed out here, and you can see the data rate changes based on the type of network you are using. You will find that a lot of the applications are now moving towards narrowband IoT, because they kind of offer the best possible compromise between all the typical mobile networks as well as the IoT specific networks. So narrowband IoT is one thing which is kind of becoming very popular. You will also find a lot of implementations of LoRa happening. So this is also kind of two very common implementations that you are getting. But what I wanted to show you in this figure is the amount of data that you can transmit for different types of networks and the ranges that you are getting. And this is how the power consumption also happens for different systems. Now you can see the units that you are seeing here are in milliwatts. Okay, so 0.15 milliwatts, 0.15 milliwatts, 25 milliwatts, 50 milliwatts, 0.5 milliwatts. So you can see that some of these are very hugely power consuming and certain others are very low power consuming networks. So if you have a very long range that you want to transmit, you will have to pick the networks accordingly. And you can see for larger data rates and for longer distances, the reasonable possible solutions that you have are limited to only narrowband IoT or LTE or 5G, which is kind of coming up. For smaller ranges and for smaller network, for smaller power consumptions, you have several options here. Okay, so a lot of applications are possible here. And if you look at the increasing ranges, you will find that Narrowband IoT kind of seems to pop up everywhere, and LTE-M also, right? So you will find that I will suggest that if you are interested in working with IoT systems, please have a look at the LTE-M and the narrowband IoT type systems. Others are also relevant. LoRa is also relevant in most of the cases, but narrowband IoT kind of seems to be kind of catching up very fast. Okay, NB-IoT. So if you are interested in reading up about this, have a look at the NB-IoT and then proceed from there. Okay, and as you can see here, the more the amount of data you want to transmit over longer distances, the more you will be using up in terms of power. Right. See, the same system also for the same distances, if your data rates are increasing, you will be ending up using more amount of power. See, 0.5 milliwatts for 100 Mbps, 10 kbps becomes 10 milliwatts. For 40 kbps, it becomes 20 milliwatts. So you can see how much difference in energy consumption or consumption this results in if you have a larger data rate. So it always makes sense to only transmit the data which is extremely relevant to you. Okay, so that's what I wanted to show you with this. This has been taken from DGKey. Can we go to the next slide? Is it okay?
Yes, sir.
Go to the next slide. So next thing that we have to look at in these terms is the latency and determinism of the constraint node networks. If you remember, we talked about the three aspects of constraint node networks. One was data rate and throughput. Second one was latency and determinism, and third is overhead and payload. So we are now at latency and determinism. So what do you mean by latency and determinism? What we actually mean is how much uh, kind of delays you are kind of expecting when the transmission is happening, right? So and what is the rate at which you can do the error correction and how you can get up with the correct output. So that is the requirement of that is basically what we understand by latency and determinism here. So you can see here that in case of constrained networks, you can have few milliseconds to few seconds of kind of latency that could be coming up. And all the protocols typically should be able to handle that kind of delays. It could be changing from application to application. So it's not like a conventional computer network where you have like a Ethernet or something. You have a fixed transmission rate, fixed reception rate, and kind of the whole network works accordingly. You could have for each network, you could be having different transmission rates. And even within the same network also, you could have certain nodes which are transmitting at a different level of latency when compared to certain others. That is going to be a big challenge, and when you are integrating that data also, it becomes very interesting as a problem. Okay, and at the most lowest level, you typically tend to consider this as a sensor fusion problem also. There are several different kinds of sensors which are measuring different parameters of the same system. You could have sensors which are picking up information at different sampling rates. So how do you integrate all of that together without creating any problems is something that you have to look at. That is the idea of a multi-sensor data fusion system. Have you heard of that, multi-sensor data fusion?
No, sir.
Hello. Oh, okay. So that is the idea behind sensor fusion or multi-sensor data fusion is that you have multiple sensors which are kind of uh, measuring parameters of the same system. Like for example, I'm trying to measure the health of a machine. Okay, so if I'm trying to measure the health of a machine, I could be measuring voltage and current signals at the rate of 50 samples per second, right? But I could be measuring the temperature of the machine maybe once every 15 or 20 seconds. I could also be measuring the vibrations of the machine at about 10 kilo samples per second. So now I have the temperature which is coming in at a different sampling rate. the current and voltage which are coming at different sampling rate, and I have vibration signals which are coming at a totally different sampling rate. So how do you join all of them together to come up with some understanding of how the overall health of the machine is? That is the idea of a sensor fusion problem. You cannot simply eliminate samples so that everything looks the same size. The data set will be of different sizes now. You have like if you can visualize it as an Excel sheet, visualize each of the parameters, the voltage, the current, the vibration, and the temperature as 4 different columns in your data set. And if the sampling rate is different, you will find that there will be different number of rows for each of the samples or each of the columns for the same given time period. If I collect data for 10 seconds, you will have different number of samples for temperature, you will have different number of samples for voltage, you will have different number of samples for vibration. So how do you integrate all of them together to make proper sense of the data? So it is kind of a machine learning problem that people are looking at. Even today, it's kind of a very interesting problem, and people are kind of working on this. So that is the idea of looking at, and that is where the latencies and other things come into picture. Okay. So the last thing that we have to look at is the amount of overhead that you have and the payload that you are putting in. Okay. So the thing is that you have a idea of transmission rate, but the actual data transmission, the actual data that is transferred is different from the total number of bits that are being transmitted. Why? Because you have something called the header, you will have the message body, and then you may sometimes have the a tail section also, which will have some error correction coding and other things involved. So the overall message which is composed will be a small quantity or a small number of bits only. I hope you understand that. You know what is a payload of a data set, right? Or a payload for a transmission. Every data packet that you transmit will be made up of 3 parts. One will be the header part. The second one will be the part where the actual data which you want to be transmitted is put in. And then you have the tail section, which will have the error correction or whatever other security related stuff that is there, that will be in the tail section. So the overall each packet will be like 200 bits or 300 bits or 500 bits or 500 bytes, whatever you may have. But the actual data content in that could be as low as about 200 bytes or 150 bytes. Remaining everything will be taken up by the header, the error correction part, etc. So the actual throughput that you are getting every time you transmit a data packet is much lesser than that. So you have to pick that also based on your requirements. Can you afford to transmit 200 bytes of data with only 50 bytes of information content? Or do you want lesser amount of headers and the tail section and larger amount of data which needs to be transmitted? But unfortunately, the problem is if you pick protocols which have smaller header and smaller tail section, the integrity of the data will become poorer. You will lose the consistency and you may have a lot of errors when the data is received at the receiving end. Okay, so that is the issue that we are talking about here. And that is what we talk about here also, small payload sizes. Okay. So that completes the 9 requirements that we have for the communication criteria. And I think I will take some questions if you have any, and then we'll stop with this. We'll continue in the next class with a totally new section. Any questions so far?
No, sir.
Sir,
Yeah, go ahead.
sir, NBAOT comes under licensed band, no, sir. So,
Need not be licensed. You can implement it in the unlicensed. If the range is small, you can implement it in the unlicensed spectrum also. You can set up a local NB-IoT system. That should be fine.
okay, sir.
Just any other questions?
No, sir.
Okay, so if there are no further questions, I will break for now. And these are the references that we have gone through. Okay, so please, this is what I was talking about when I was talking about the RFC 7228. You can go here and check the specific RFC, or you can go to IETF and download it from there. And there are 3-4 more references which I have listed on, and there are some references which are listed at the bottom of the slide if you see this. So I have lifted out wherever I have taken images or something else, I have just listed out where they are. So these are all articles based on which the images are present, so you can go through that also. Okay, so you can see I have listed out all those. So please look at the comments section or the notes section under the presentation also if I am uploading it as a PPT. If I'm uploading it as a PDF file, I'll add these references in the references section. So you can click and go there and read more about it. Okay, this is apart from the textbook that we are using. The textbook is the one by Cisco. It's already given in the syllabus. Other than that, whatever I'm using, I'm giving you as references here. Okay. So I think if there are no further questions, I think I will break for now. Just 1 second. Give me time to download the attendance. Let me see. And one small thing, just give me a second. When is your exam starting? Midterm exam?
On 15th, I guess.
Okay. Just 1 second. I just checked the consolidated attendance so far, and what I'm seeing is Satindra has stopped it. The course, is it number 14?
Yes, sir. He stopped last year.
Okay. And I am seeing some of the cases where the attendance is about 70%. So please make sure that all of you attend that. I don't want to give the names, but there are people who have attended only 70% of the classes so far. So please make sure that all of you attend it. And when I'm taking attendance, please make sure that you are all there. Otherwise, it will be difficult for me to recommend you for your end semester. Please make sure that all of you attend it. Okay, fine. So I think if we are done here, then we can stop now. Thank you all for attending. We will continue in the next class, and hopefully module 4 will have some other simulation studies, etc., which I'm planning to give you. Let's see. Okay, fine. Thank you all for attending. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.